Hello, everyone. The topic I want to introduce today is GFLOPs-aware AI model architecture optimization, GoP-mode real-time detection, and the HiTag auto-labeling system. Outline contains introduction, 4 techniques, conclusion, and industrial applications. The market for professional service robots is expanding year by year. Service robots require object detection, object tracking, and hazard detection to move in crowds. However, due to cost considerations, it's impossible to install supercomputers on robots. Robots can provide services in the store, including product location navigation, accompanying customers, and assisting in product delivery, or proactively approaching to give promotion messages. The robot is equipped with a sensing system, including a video lens, ultrasonic radar, or LiDAR, and continues to perceive the surrounding environment, including stationary and moving objects. Due to the huge amount of perceived data and the endless supply property, as well as the extremely complex calculations of modern AI models, it's necessary for us to design an accurate and fast AI detection system to be applied to mobile service robots. According to this goal, we achieved the following results. Reduce model calculation by 90%. Increase detection accuracy by 2.7%. And increase execution speed by 31%. This enables our detection system to reach a speed of 30 FPS on JSON Nano with a high accuracy. In the following, let's check out each single technique working behind. First, we increase the detection accuracy by increasing the amount of parameters. During the design, we keep the original amount of model complexity to maintain a similar execution speed. By adjusting the stride size of each neural layers and the number of convolution sets. On this slide, you can see the figure for the network architecture, the table for variable definitions, and the equations for the spatial domain design methodology. By using this methodology, we can decrease the computation complexity by 50%, increase detection accuracy by 2.7%, and increase execution speed by 72%. When compared with the famous YOLO V3 model, Agile V4 model achieves both higher accuracy and execution speed. The product of accuracy and speed indicates that Agile V4 outperforms both YOLO V3 and YOLO V4 in terms of efficiency by at least 54% of improvement. Although we have already optimized the AI model in spatial domain as much as possible, the execution speed on JSON Nano is still behind the real-time target. Besides, the service robot application requires hazard detection, which inspires us to develop the dynamic acuity detection similar to creatures. These two demands call for the use of temporal domain information. Therefore, we propose an advanced tracking architecture which requires less computation burden. The architecture can predict the position of each object accurately without detection. After our optimization, the tracking network is lowered down by 50% of computation complexity. The execution speed on this nano is increased by 51%. We have implemented accurate object tracking without ID switching, as shown in the video on the left-hand side. We can see that each object is assigned with an individual ID number, even paths of object intersect. The presented system can track each object well. Based on such precise tracking information, we can predict the lateral approaching behavior of each object in advance, as shown in the video on the right-hand side. The bounding boxes highlighted in green indicates that these bounding boxes are approaching the future path of the service robot. With such useful information, we can implement intelligent closing technique for service robots, allowing them to wisely pass surrounding moving objects like a human. The object tracking information can be further used to remove temporal redundancy. We call it group of picture mode acceleration. In GoP-mode, frames are classified into I-frames and P-frames. Object detection is executed on I-frames only. As for P-frames, the results are predicted via our AI object tracking net. Since the execution time of prediction is much shorter than that of detection, the value of frames per second has been greatly increased, while remaining the overall detection accuracy the same. By setting P-frame number as 4 to form up an 1i 4P GOP structure, the complexity can be reduced as much as 80%. Such complexity reduction results in 462% speed up in terms of frame rate. One more fundamental but critical technology behind these successful results is auto data labeling. We adopted AI engine to replace pure human data labeling to save time. Besides, we designed original user graphic interface called HiTag to make it easy for users to use. HiTag includes two parts, iLabel and iEvaluate. iLabel is designed to generate pre-labeled data for accelerating ground truth establishment. On the other hand, iEvaluate is to auto-evaluate labeling quality based on ground truth. Here, we capture two frames during iLabel and iEvaluate usage as examples to illustrate the tools. Finally, let's conclude this talk. The presented system achieves 30 FPS when executed on an economic platform called Jetson Nano. The detection accuracy reaches 58.4% on MS COCO dataset. The total computation complexity reduction is as high as 90%. The excellent speed-up improvement is as high as 12.31 times over and older. Please check out more details about our system through the QR code. The applications include mobile service robots, autonomous mobile vehicles, disinfection robots, logistics robots, and sweeping robots. The technical spec is as described in conclusion. According to market analysis from the International Federation of Robotics, global annual sales of service robots reached $11.2 billion, a growth of 32%, and will continue to grow in the future. Please contact us if you are interested in our solutions.